All right, this is Unit 1 Test Review Part 3. Let's talk quadratics. All right. And I think I'll start by reviewing the different forms of quadratic. The first form is vertex form, or sometimes people say completed square form. And that's when you have your function or your quadratic in the a x minus h squared plus k form. And what's great about this form? Well, it's pretty easy to find the vertex. The vertex is hk. And just other things to remember, if a is greater than 0, the parabola opens, well, I don't need to say parabola. I'll just say opens up, which means we've got a minimum. If a is less than 0, the parabola opens down, which means we've got a max. And another important feature is the axis of symmetry, which is the vertical line that divides the parabola into two symmetric halves. And that is always x equals h. Again, that vertical line going through the x coordinate of the vertex. And let's see if there's, and then it's, maybe I'll say about it here. For parabolas that open up or down, the domain means what I can put in for x, no restriction, so all reals. The range, however, so if it opens down, meaning we've got a max, the range is going to be negative infinity to the y coordinate of the vertex. Again, it has a max, whereas if it opens up, that we got that smiley face looking parabola, so opening up versus opening down, then it has a min. So that min will be the y coordinate of the vertex all the way to infinity. And if you're confused about how to get it into completing square form, check out my video on putting a quadratic into completed square or vertex form. There's a review of that. Okay, let's go on to next form. Let's talk about root form. Now the roots are the x-intercepts, or you could also think of them as the zeros or the solutions of the parabola. And so in this case, I have the roots are r1 and r2. I have a x minus r1, x minus r2. And again, r1 and r2 are my zeros or x-intercepts. So in this case, it's in this factored form. And what's easy to come out of this? The x-intercepts. Those pop right out. But I don't want to have to FOIL it out and complete the square to get the vertex in this form. But the vertex I can just get by taking the average or the midpoint of the roots. And once I have the x coordinate of the vertex, then I can just plug it back into the function to get the y value of that vertex. So again, you don't have to go back to a different form in order to find the vertex. All right, so the third type is standard form, which is f of x equals ax squared plus bx plus c. And in this form, the easiest to find in this form is the y-intercept, because it's just going to be c. When x is 0, then the y value is c. So the y-intercept just pops right out. But I'm going to argue we also don't have to go back to the completed square form or root form to find what the x-coordinate of the vertex is. And if you remember how we derived it in class, is we learned that, the x-coordinate of the vertex is negative b over 2a. So particularly if I have, in standard form, if I have some ugly coefficients of x squared or b, I'm going to want to use negative b over 2a. I don't want to complete the square. Certainly don't want to try to find the roots, perhaps, because those could be ugly too. So I'm just going to do negative b over 2a to get the x-coordinate of the vertex, or maybe I should say x-coordinate vertex, or that h value if we refer to the vertex form. And then, so the vertex is going to be negative b over 2a, comma, just put that x-coordinate back into the function to find the y-coordinate of the vertex. So those are your three forms. And from each form, you should be able to get the vertex without manipulating it to get it to a different form. Okay, so now let's talk about solving quadratics. And remember, solving quadratics, you're really finding the x-intercepts, also known as the zeros or the roots or the solutions of the quadratic. So for me, and everyone has their own comfort level with this, but for me, solving quadratics, I'm comfortable factoring, so I always see, can I factor? And if I can't easily factor, then I'm going to do quadratic formula. I rarely complete the square. To me, it's just too tedious to solve quadratics, and it's easy to make errors, but you can complete the square. So I'll just say complete the square. But again, I don't go there. Instead, if I can't factor it easily, I'm going to use the quadratic formula. And remember, the quadratic formula is this. Again, we derived it in class. And these A, B, and C just refer to the coefficients when your quadratic is in standard form, like this. Okay, so there's two roots here. One root is negative b plus square root of b squared minus 4ac over 2a. And the other root is just negative b minus. Well, sometimes it's helpful to know what to anticipate in terms of the number of roots and what type of roots to expect when I have a given quadratic. So in that case, something called the discriminant is very useful. And the discriminant is what's under the square root. It's equal to b squared minus 4ac. Now, if that's positive, so if it's greater than 0, then I'm not going to have any negatives under a square root, which means I'm not going to have this imaginary roots, which aren't actually x-intercepts, so on my graph. So if it's greater than 0, I'm going to have two real roots. I'm going to say distinct, because one will be plus, one will be minus. Negative b plus, whatever that is, negative b minus, whatever that is, over 2a. So two real distinct roots. And kind of a subset of that, if b squared minus 4ac is greater than 0 and a perfect square, that means everything will be coming out of the square root. So I won't have anything left inside. So that means I'll have two rational distinct roots. And whenever you have rational distinct roots, it means you actually could have factored that baby. So it's okay if you didn't, but it tells you that, you know what, I can factor this if I'm not getting anything left inside the square root. All right, what about if it equals 0? Well, if it equals 0, you're just going to have negative b plus or minus 0 over 2a. So you really only have one x-intercept, which happens to be negative b over 2a. That should give you a clue. Wait, negative b over 2a, where does that come from? That was the x-coordinate of the vertex when it's in standard form. So if b squared minus 4ac equals 0, I have one x-intercept, and it happens to be the vertex. It's the only way that can happen. If b squared minus 4ac is less than 0, that means I'm going to have a negative in a square root. It's going to involve i's, so I'm going to have no real x-intercepts. And we're going to say, since we're only graphing over the reals, we're just going to say no x-intercepts. If I ask you to solve over the complex numbers, then you would give me an answer in terms of I. But in terms of a graph, there's no real x-intercepts. Okay, so that's the quadratic piece, but attached to this, I want to do a couple other things. I want to talk about I a little bit and remind you about that, and then I just want to talk about a few applications. All right, so let's review a little bit about I, because I mentioned it with quadratics and solving quadratics, and sometimes you have a negative in front of the square root. So a little recap on that. So on I. So I is equal to the square root of negative 1, or I squared equals negative 1. So what about some problems like the following? Because to be a complex number, or all numbers can be written of the form a plus bi. Now with real numbers, b is 0, so you don't have any I piece. But you can't write a number with anything higher than I to the first power. So that's one piece. The other piece is because I is a square root of -1, so it involves a square root, you can't have to be fully simplified, you can't have I in the denominator. So let's do two types of problems. I'll just simplify as much as possible. All right, so let's do this first one. What if I said simplify I to the 85. So clearly bigger than I to the 1. So, and people have different ways of approaching this. Some people think of divide it by 4 and honestly, in my Honors Algebra 2 class, I do talk about it that way, but I think the easiest way is, since we know I squared is -1, let's just rewrite this in terms of I squared. So 2 goes into 85, like what's the closest without going over? In other words, how I squared to what power gets as close to 85 as possible, and that would be 42. So that would get me I to a power you multiply. So that would get me I to the 84. So I just need to multiply by one more I to get I to the 85, because with the same base you would add exponents. So again, I'm rewriting I to the 85 in terms of I squared. And the reason I do that is I squared is just -1. So I replace that I squared with -1. And -1 to an even power is just going to be 1. So this is just going to equal 1 times I or I. Now, if I had had -1 to an odd power, then it would be -1 and I'd have -I. So, and you'll find, I'm trying to think in what pack, I think it's in 1.3, you'll find more of these types of problems, just simplifying I to higher powers. The other type of problem, again, just some mechanics here, is if I ask you to simplify, say like 3 plus 2I, let me think, like, I don't know, 5 minus I. All right, so problem here is there's no common term that I can factor out of everything, but I can't have I in the denominator because, again, I is just equal to the square root of -1. So to get that out of the denominator, or to rationalize, I have to multiply by the conjugate, which is 5 plus I. Okay, so in doing so, the denominator becomes 25 minus I squared, and then the numerator, a little more annoying, gotta FOIL this out. Oh, so by the way, denominator, I went a little fast there. The purpose of multiplying by the conjugate is you want to eliminate the i's, so notice the middle term goes away. You've got -5i and +5i, so that middle term goes away. All right, so in the numerator, I have 15 plus 3i plus 10i plus 2i squared. All right, oops. Let's now simplify. Remember, I squared is -1. So in the numerator, if I have 15 plus 2i squared, that's really 15 minus 2, or 13. So I've got 13 plus 13i divided by 25 minus I squared. But remember, I squared is -1. So 25 minus -1, or 26. Which works out nicely here because these all have a common factor, the common factor being 13. So I can take 13 out of everything, so 1 plus I over 2, or you could write 1/2 plus 1/2 I. Okay, so those are just kind of remembering the I stuff. Okay, finally, the applications of quadratics. The main kind of nuance. Okay, so let's talk about applications here of quadratics, and there's different types. There's, you could end up with a quadratic that, you could end up with just a word problem that the end result happens to be a quadratic. I think we did one with a triangle, and when you solve using Pythagorean theorem, you end up solving a quadratic. The more interesting ones, though, are the when you have this constraint equation, like those fencing problems we did, and then you're trying to maximize or minimize something. So let's do a problem. I'm going to make one up. Let's talk doggy daycare. And say you want to separate in your doggy daycare and create this fenced-in yard where you separate small, medium, and large dogs. And so let's say, I don't know, so let's say you can use 200 feet of fencing. Let's say you have 200 feet of fencing to work with. Okay, so that's your constraint. But then you want to, based on that constraint, though, you're really looking to maximize the total area fenced in. So let's first create our constraint equation. So just sign some variables. It doesn't matter, honestly, which is x and which is y. So I can, in terms of my fencing, I can say, all right, 2y plus 4x, or really the perimeter here, is equal to 200. That's my constraint. And then, but the equation I ultimately want to work with, if I want to maximize my area, is x times y, my total area, by the way. All right, so since I want to work with the area equation, I really want to write that area equation in terms of only one variable. So let's go back to the constraint equation and let's simplify a little bit. We can divide everything by 2. So y plus 2x equals 100. And let's solve for y in terms of x, because then I can substitute in for y here. And that allows me to have an area equation only in terms of one variable. And you should notice, if you FOIL this out, that, oh, good, the representing the area is a quadratic that opens down, since the a value, the leading coefficient, is negative. So this indeed will have a max. So if I want to find the dimension that will get me a max area, well, then I want to find the x coordinate of the vertex, because that will give me the x dimension that gives me a max area. So the x dimension, or the x coordinate of the vertex in this case, negative b over 2a, or this is going to be 25 feet. Okay, that's the x dimension. To get the y dimension, you're not plugging it back into a of x, because that'll get you the max area, which we do want too. But if I want the y dimension, I'm going back to the relationship between the two variables in terms of the dimensions. So y equals -2 times my x dimension plus 100. So it looks like the y dimension is 50 feet. So the dimensions that give you a max area are 25 feet by 50 feet. If I want to find the max area, I can either multiply those two together, or I can plug 25 back into this area equation. You should get the same thing if we've done it correctly. So maybe I'll just, since I found both the x and the y dimension, I'll just say the max area is 25 times 50, and 25 times 5 is 125, and I'm just going to add the 0, so feet squared. So just keep straight what a of x stands for and what the x in that stands for. The x is the dimension that gives you the max area when you're finding that x coordinate of the vertex. And when the y value coming out of a of x is actually the max area. If you want the y dimension, you got to go back to the constraint equation. Okay, so now I'm going to wrap up quadratics with that.